All right, so covalent bonding. When we have a group of atoms that are held together covalently, and they are neutral, such as water, bromine, we call that group of atoms that are held together covalently a molecule. This term only applies if they are held together with covalent bonds. When we have something held together with covalent bonds, the littlest chunk of that stuff is a molecule, and those are molecular compounds. So, for instance, molecular compound. Because the hydrogen and the oxygen are held together with what kind of bonds? Covalent. So it's a molecular compound. Let's look at sodium chloride. What kind of bond was that? You have it in your notes. Go back as we looked at the electronegativity difference. What kind of bonds were holding sodium chloride together? Ionic. Can you have a molecule of salt? No. There are no molecules of salt because it is held together with ionic bonds. Water, on the other hand, you can have a molecule of water because it's held together with covalent bonds. That's the big difference between a molecular substance and a non-molecular substance. Okay? It's only a molecular substance if it's held together with covalent bonds. Okay, CO. Look up your electronegativities. What kind of bond is CO going to form? Okay, so we've got electronegativities of what? 2.5, 3.5, difference of 1, which makes it what kind of bond? Polar covalent. Okay, so we can have a molecule of CO. We have a molecule of CO. CO is carbon monoxide, dangerous stuff, produced very often as a result of burning hydrocarbons. Like if you have one of those little natural gas fireplaces, you have to worry about the formation of carbon monoxide in your house, poisoning you and killing you all in your sleep. Don't let that worry you too much. They just have to be vented correctly. Okay, so we've got molecules of CO. Well, they form, remember how we talked about in the last chapter these wild, crazy, sort of high-energy, unstable atoms running around the world out there? How much better off they'd all be if they could just settle down a little bit, be a little bit lower energy, be a little bit calmer. This may have been something that you have observed. Maybe you've had a friend who was just a little kind of too wild. And then they find their sweetie pie. Aw, cutie pie. And they're much calmer. Suddenly, they're just calmer. They've got their cutie pie. They're nicely bonded. They're calmer. This is good. It's not such a stretch to use this metaphor for atoms that are bonding and forming molecules. So it's a dance. It is this literal dance between attraction and repulsion. So proton-electron attraction, opposite charges. Protons love electrons. Love them. However, deep down there in the center of each atom is that tennis ball of positivity, the nucleus. Well, one tennis ball really hates another tennis ball. And surrounding those tennis balls, you got two electron clouds. Well, that's all negative and all negative. And negative plus negative is also repulsive. So the metaphor is this. There's that person that you've always thought was just adorable, cutie pie. You're very attracted to cutie pie. Cutie pie is wonderful. Cutie pie is adorable. Cutie pie is so overwhelmingly attractive. You want nothing more than to just be near cutie pie. Oh, Cutie Pie. Sadly, Cutie Pie has a best friend who is the most repulsive human being you have ever met. It's so sad because Cutie Pie is so sweet. Cutie Pie is so attractive. You just want to get close to Cutie Pie. And then there's best friend. Ugh! The thought of being near best friend makes your skin crawl. Cutie Pie is wonderful. Cutie Pie is just everything good that could be. You would like to bake cookies with Cutie Pie and sit next to Cutie Pie on the couch and watch movies and eat popcorn and go for bike rides and hang out on hillsides looking at clouds and just talking because Cutie Pie is awesome. Best friend is a wretch. Best friend is a horrible human being. Best friend might as well have like pus-filled maggots coming out of their skin at every single moment of the day. They are horrible. They are awful. They are disgusting. You do not want to be in the sight of best friend, let alone have a conversation with best friend, because best friend is a jerk. Best friend is mean. They are nasty. They say horrible, awful, nasty things. They insult people. Plus, they're just stupid, and everything they think is wrong, and they're just awful in every way imaginable. Ugh! Sadly, Cutie Pie and best friends, man, they've been best friends since, they were 3. Cutie Pie doesn't really want to go places without best friend. You take Cutie Pie, you take best friend. Hey, this is my best friend. You want to hang out with Cutie Pie, you're going to hang out with best friend. It's just the way it is. So there is this perpetual dance of attraction. Cutie Pie! Best friend. Huh? And you want to get as close to Cutie Pie as you possibly can. But you don't want to get any closer to best friend than you have to. There is a powerful attractive force. Cutie Pie! And there is a equally powerful repulsive force. Because best friend is awful. So this is the dance. This is the dance that's occurring between two atoms. This is the dance that's happening. So every time carbon approaches oxygen, they are less stable on their own. They need to bond to create some stability. They will be at lower energy once they do that. And they get about so close that attractive force pulls them together, and then they get to a point where, boing, you see best friend and you kind of take a step back. The repulsive force of their two nuclei start to push them back apart. The repulsive force between their two electron clouds start to push them back apart. But there's still that attraction of nucleus for electrons and nucleus for electrons. So what they do, you can imagine two objects moving towards one another and then sort of recoiling. And there's a point where they sort of do this dance, and then they come to a distance that they can live with. They come to a distance where they can live with. That's where the bond forms. The bond forms at that point of balance. This is like a teeter-totter, to use another metaphor, where you're balancing attraction, repulsion, and at some point you get a balance. That's where the bond forms. So bonds form where energy is at a minimum. Let's draw that. Remember, we talked a little bit about this as being a metaphor. One good metaphor is the hillside for potential energy. When these things are not bonded to anything else, they have very high potential energy, which means they're unstable. This is a cliff on the top of a rock hanging over Route 7. Rock slides possible. Okay? These things aren't stable. They've got way too much potential energy. If we can get them down here to a flatter spot, and they can bond, they will be much more stable. Now, the repulsion of the nucleus for the other nucleus can push these things back up the hill a little bit. But when they finally get to a point where the attraction and the repulsion are balanced, they're going to form a bond. Now, the closer they get, the closer that attraction pulls them, the more powerfully repelled they are, because it depends on distance. The further apart they are, the less that repulsion is working and the more the attraction is working. So they get to that middle point and they form a bond. Okay? And it's at the point where they're going to be most stable. It's where their lowest energy. This is where their energy is lowest. That's where they're going to be stable. And it's going to be a little bit different for every single pair of atoms. For every two different kinds of atoms, for every two different elements, that's going to be slightly different. Jumping back, I do apologize. We will start working a little bit in this chapter, but a lot in the next chapter with chemical formulas. And for molecular compounds, remember molecular compounds are held together with what? They're held together with what kind of bonds? Covalent. They form molecules, yes. So molecular compounds are made up of molecules. They're held together with covalent bonds. We have a formula, and that gives the actual number of every kind of atom in a molecule. We have things like O2, H2O, C6H12, O6. That's a molecule. One molecule of sugar. Glucose, actually. C6, 6 carbon, 12 hydrogen, 6 oxygen. And you should have used chemical compounds in physical science. You probably, or chemical formulas. You probably did some formula writing. You probably balanced some equations, depending on who you had and when you had them. We're going to come back to these, but you should be aware that in a molecular compound, it's the actual count of atoms in a single molecule. And this graphic just kind of shows the potential energy, that same hillside that we talked about, where something that isn't bonded tends to have very high potential energy. It tends to be very unstable. It's that rock on a cliff hanging over the road. And when it bonds, it significantly lowers its potential energy, and it's much more stable. The distance, the place that they arrive at, and that dance of attraction and repulsion between cutie pie and best friend, is the bond length. And that length is different in different compounds. It can even be different between two of the same atoms. So carbon is notorious for this. Carbon is awesome stuff. Carbon loves to bond to other carbon. The bond length is not always the same. We're going to get to that in a second. So we can talk about bond length and we can talk about bond energy. Do you remember the metaphor that we used with solids, liquids, gases? We won't even go into plasmas. Where if water, for instance, goes from being a solid to a liquid, we have to put that much energy into it. If it goes from being a liquid to a solid, this much energy is going to fly off out into the world. Well, the same thing exists here. The difference between this amount of potential energy way up here when it's unstable, it's that cliff, that rock on a cliff overhanging Route 7, and this amount of energy when it's nice and low and stable, that difference is the bond energy. That's the amount of energy that's contained in that bond. Okay? And when you break that bond, it typically takes some energy to get it to start to break. Once you break that bond, you release energy. Okay? You actually release the energy that's in that bond, and you can get a lot of work done with that energy. A lot of you probably got to school this morning by breaking bond energy between carbon atoms. Yes? Anybody get to school that way? Breaking bond energy between carbon atoms? If you came in a motor vehicle that was powered by gasoline or diesel fuel or vegetable oil or natural gas or any of those things, the energy that was doing the work of moving the tires on the vehicle you came in, that energy came from breaking the bonds between carbon atoms in gasoline or diesel or kerosene or vegetable oil or, paraffin, if you have a paraffin-powered wind-up vehicle that you used to get to school this morning. And actually, even if you used a goat cart, the goat was breaking bonds between carbons in the form of grass. The goat cart, yes. Much more reliable on really snowy mornings. Okay, so we can talk about bond length and bond energy. Do you think there might be a relationship? So I have some rubber bands that were loaned to me by my brave assistant. And I am going to give you some rubber bands. So as you found when you were stretching your rubber bands, the amount of stretch that you put into it, the further out that it is, the more energy it takes to hold it there, right? When that rubber band gets fatter, when you've got 5 rubber bands on there instead of 1, it's going to hurt more when it snaps back. Those shorter bonds actually contain more energy. So, if we have 2 things that are bonded like this versus 2 things that are bonded like this, oops. These are covalent, remember. This is carbon-carbon, so this is purely covalent, identical electronegativities. Carbon is famous for bonding to carbon, and it's also well known for double and triple bonding. When you make multiple bonds, they tend to get shorter and shorter and shorter and shorter. A double bond is going to be shorter than a single bond, and a triple bond is going to be shorter than a double bond. And those shorter bonds have got a lot more energy contained in them. Now, if you look at the chart here, and this is reproduced from your book, this chart of bond length and bond energies, I only expect you to have the top half memorized, and I think by tomorrow we'll do it. You don't really have to memorize a chart of bond length. That's ridiculous. That's stupid. I would never ask you to do that. That's so silly. I like to say things like that and watch who goes, oh, okay. Because I'm messing with you. It's okay. It's good that you would do that, but it's ridiculous. The big thing I want you to understand, though, is when we double up bonds, when we put 2 rubber bands on instead of 1, we can't stretch it out as far. And when we double up bonds, when we put 2 rubber bands on instead of 1, it takes more energy to stretch it out to the same distance, and in most cases, you can't get it out to the same distance. So that double bond is going to be shorter, and it's going to have more energy in it. And when you get to a triple bond, it's going to be shorter yet, and it's going to have more energy contained in it. That's the big thing I want you to understand. Now, how many of you have ever heard of MAP gas? How many of you have heard of propane, first of all? Propane! Okay. Monkeys eat peanut butter. Propane is 3 carbons tied together with a bunch of adjacent hydrogens. Nice stuff. Gaseous, it can be compressed down to a liquid, burns nicely. We use it for all kinds of things, furnaces, hot water tanks, dryers, barbecue grills, little propane torches if you're doing some plumbing work or if you're lighting things off. Or if you're a 13-year-old boy in a 40-something-year-old engineer's body for a potato cannon. So let me tell you about my friend Mike. He's not really my friend, he's more my husband's friend, but Mike is an engineer. And there's a whole little sort of tribe of engineers. Smart guys, all of them, and women, smart people. With access to high-powered mathematics. So you all know what a potato cannon is. We have some sort of cylinder with some sort of tube, and we cap that cylinder, and we have some sort of gas that can be ignited, and we ignite the gas, and it goes boom, and the potato, which is firmly jammed in the end of the potato cannon, goes shooting off into space, and we all laugh really heartily, and we spread shredded potatoes all over a large field, right? You know how this works. So Mike built a potato cannon. And he was not satisfied with building any potato cannon. Oh no, he's an engineer. He was going to build the mother of all potato cannons. No Aquanet for Mike. No ether. No, no, no. Mike did all the calculations. And I tell Mike that I talk about him in chemistry. He knows that I tell this story. Mike did all the calculations because the forces that occur when you ignite certain gases are really high. And your materials have to be able to withstand the forces that you're going to generate inside the potato cannon. And different chemicals have different kinds of bonds and different energy. And when you break those bonds by, say, lighting it on fire and making it go boom, then that energy is released, and different amounts of energy are released, and different amounts of energy mean different forces on the object. So Mike knew all this because, remember, he's a smart guy. So he did all of his engineering calculations, like pages of calculations, seriously, looking at expansion rates, and, there's some chemistry, there's some physics. It's good stuff. It's really good stuff. And he did all the engineering, and he built his super potato cannon to be propane-powered, baby. Propane-powered potato cannon. What 44-year-old engineer would not want a propane-powered potato cannon? This guy is the hit of every party. Woohoo! Here's the propane-powered potato cannon. So remember what we said about propane? 1 carbon, 2 carbon, 3 carbon. Single bonds. There's a lot of energy in carbon bonds. I mean, most of our economy is based on breaking carbon bonds for energy. That's what we're running this world on right now, is breaking bonds between carbons. When we talk about hydrocarbons, we talk about oil and coal and natural gas. That is all carbon-carbon bonds. We are running this world on carbon-carbon bonds. And Mike was running his potato cannon on them too. So, you've all heard of propane. You're all familiar with propane. You could all probably go home and lay hands on propane. Have you ever heard of MAP gas? M-A-P-P. It's a trade name, and I forget what it means. It's a trade name. I don't remember what it means. And I didn't used to know what MAP gas was until Mike showed up with his propane-powered potato cannon. And Mike showed up at a bonfire with his propane-powered potato cannon and his bright, shiny, new red car. And Mike was very, very concerned about nobody scratching his car. We were parking in a field, Hey, back off. Don't open your door near my car. Hey, stop. Okay. And Mike, with all the glee of a 3-year-old on Christmas morning, said, I brought MAP gas. And I said, okay, because I didn't know what MAP gas was. I said, what's MAP gas, Mike? And Mike said, oh, it's great. Now, Mike, mind you, is not a chemical engineer nor a chemist, though he had done some pretty heavy-duty chemical mathematics for his propane-powered potato cannon. And he said, MAP gas is awesome. It's got more bang for the buck. I said, oh, cool. He said, yeah, it burns hotter. It's a little more oomph. Okay, cool, great. So, they had a propane cylinder. They fired off the propane-powered potato cannon several times. It was spectacular. Shredded russets all over the field. Yee-haw! Then they got out the MAP gas. Now, it just so happened, I had gone down to the house to use the bathroom. Boy, was I happy about that later. So, Mike, the very smart guy who was not a chemical engineer, filled that sucker up with MAP gas. And then he pulled the trigger. Now, Mike, being a smart guy, was setting off the propane-powered potato cannon out in the middle of the field, far away from the circle of people sitting around the bonfire, out in the middle of the field by his car where he had all his stuff. And what everybody around the fire heard was not the familiar of a potato flying in shreds up into the brilliant night sky, but they heard boom, crash, bang, which was Mike's potato cannon blowing up into 1,000 shards. Then the metallic bang was all those shards hitting his car. And then there was silence, while friends called out in earnest worry, "Mike? Mike? Mike!" And there was no answer. Now, I don't know what you know about PVC shrapnel, but it can go through your jugular pretty effectively. So there was some legitimate concern until everybody got to Mike. And it turned out Mike was not answering because Mike couldn't hear anything, and he didn't really hear much of anything for the next hour or so. Turns out, MAP gas, well, it's got some carbons, but instead of single bonds between those carbons, MAP gas has some triple bonds. So MAP gas, in fact, has one single bond, one triple bond. MAP gas, in fact, does, as Mike so aptly put it, have a whole lot more oomph for your buck. It's got a heck of a lot more energy. Heck of a lot more energy. Mike had done all kinds of very careful calculations to make sure that his propane-powered potato cannon had the right thickness of PVC pipe and had adhesives that would hold the sections together under the tremendous forces unleashed by igniting propane. However, he was no longer using propane. He was using something with a triple bond in it. And that very night, in that very field, I said to Mike, "I'm going to look up the chemical formula for MAP gas. I bet that sucker's got a double bond. Oh no, it's got a triple bond." Oh yeah, they don't sell MAP gas commercially anymore. We still have a few cylinders in the garage because it's useful if you have a little propane torch that you're using to do plumbing work. If you use a MAP gas torch, you get more energy out of it. You get more thermal energy. You can get that piece of pipe hotter faster because you're now looking at a multiple bond. When you break that multiple bond, you get more energy out. So, the takeaway, multiple takeaways. Don't be Mike. Number 2, multiple bonds have more energy and they're shorter.